Okay, so I would like to introduce the next speaker, Gabriel Synnaeve. During his preparing the slide, okay, it's working. He is actually having an interesting background. Gabriel got a PhD in the University of Grenoble. And he's actually first started to work on the logic programming and then moving to game AI. And then later, he started to do speech, unsupervised Bayesian modeling with Emmanuel Dupont, and then joined Facebook. And today's talk is one of the exciting topic called wav2letter. And I think Gabriel may also present more details, but this is one of the real end-to-end. Some of the people, including our team, we actually have some shortcut, especially for the feature extraction, but some of their work is actually starting from waveform. So it's quite a unique but very effective approaches. And in addition, since this is a good culture in the Facebook, I believe, they usually, Gabriel and colleagues usually also make it public, open source, so we can enjoy their outcomes every time they just publish. So today's his talk, let's enjoy.
Thanks for the great introduction. Okay, so I'm going to talk about what we do in the wav2letter team, and also the many meanings of end-to-end ASR. So there's always this debate about what really is end-to-end, and can have many meanings, and we do different types of research and studies on that, and I'll go through some of those. So what is actually truly end-to-end, I would say, is learning in infants, right? Because learning in infants, over a period of like 14, actually 20 months, they kind of learn to speak. And they learn with between 1,000 and 5,000 hours of speech that is not really supervised, like weakly supervised sometimes, but mostly unsupervised. And they have to learn both the phonetics, the segmentation, the lexicon, all of that at once. So, I mean, if we really want to be absolutist in terms of end-to-end training, that's really, we have to look at infants, right? And that's kind of where I come from. When I studied speech, I worked with Emmanuel Dupont, mostly on unsupervised speech. So I'm kind of tainted with that along all of my research. So just so that we're clear, in general, speech recognition, everybody agrees on that. What we have audio coming as input, we have transcription going as output, sometimes some features, some sequence-to-sequence model in the middle. So there are some difficulties because the sequences of audio are long compared to the size of the outputs. The vocabularies are big, they are long tail, so there are a bunch of difficulties coming with ASR. Traditionally, you have an acoustic model that outputs some sub-word units, like phonemes, for instance, in this case, if they are acoustically relevant, or even now more and more letters and graphemes or word pieces. And then you combine that with a decoder and an external language model, and that's how you produce a transcription, right? And so already, like the most extremist people would say, if you have a decoder, it's not really end-to-end. But what I'm kind of more interested in is actually end-to-end training, right? So meaning we can have whatever kind of system we have, but there needs to be moving parts in it. There needs to be weights all along the way, and you can train them from the transcription. So this question, what is really end-to-end? Well, we're going to look into a bunch of different things, but it could be from the raw waveform. It could be directly to letters or graphemes, something that is not like described by linguists. It could be directly to words, which is a great thing, like Karen talked about right before, and we're going to see a bit about that. We could also say, there are some people saying it's not really end-to-end if we have an external language model or not, or if we have some beam search, or if we are and so one very basic thing for end-to-end training to me is like, it's actually to train without an alignment, right? If you train with an alignment, you need a step before, so it's not really that end-to-end. Okay, so but why are we interested in end-to-end training? So to me, it's because it's simpler. it's simpler to optimize, it's simpler to apply to different languages, simpler to scale up, because if you have some phonemes, you need to have phonetic dictionaries for all the languages, for instance. So to me, really, it's simpler. But I would make an argument that it's not just because simpler is good, it's actually because when we do research, in particular when we do machine learning research, we need to look at experimental phenomena. And it's a good way to have something simple to be able to isolate them and study them in isolation. And so because of that, I would say end-to-end training is really also more hackable for research. You can, it's easier to do transfer across tasks, it's easier to do many tasks at once, or to lift some of the supervision, which is, I think, where the whole field is going and should be going. So very briefly, I'll introduce some things about wav2letter in order and some recent works. So the first thing I want to present is based on the first two papers we did when we started kind of this project, where we said, okay, we're going to go directly to graphemes. And we were also not so satisfied with CTC. So for a reminder, CTC is connectionist temporal classification criterion. So it's a way to train model on sequences when you have the transcription but not the alignment. And so in the first papers, what we did is we said, okay, we're going to do letters instead of phones. We are not the only ones to do that, and not the first ones either. But we wanted to do that also with like a principal way to train things. So to give an example of CTC, one of the problems we identified with CTC is that you are basically, when you are training it, you are basically always just maximizing a score. You are maximizing the score of all the possible paths leading to the correct transcription. And the way this doesn't blow up, because if you just maximize something in machine learning, most often you just blow up your weights, right? The way this doesn't blow up is that it's normalized per frame through here the softmax classically, but it could be other functions. And the problem this gives is you have this more complex graph because you need blank labels and because you need this, and you have more complex optimization because you need this normalization. So the first thing we did is try propose a new loss. So, for instance, if the target is a CAB, we do exactly the same as in CTC, which is we maximize the score. So this score, sorry, where is the letter? We maximize this score, which is the score for all the possible correct transcriptions. And we minimize another score, which is the score for, okay, so for this score, maybe I went a bit quickly. For this score, we have emissions, which are the output of the neural network for each of the frames, for each of the target vocabulary, and transitions. And one thing that is different also with CTC is that in CTC, the transitions are uniform, they have no weights. Here in HD, those are trainable. So you have a diagram language model that you can train along your criterion on your vocabulary. And then what we minimize is all the possible paths. So this is this term in the loss. All the possible paths through the graph. So in this case, you no longer have a locally normalized model, a frame-by-frame normalized model, but you have a model that is normalized through the whole sequence. And it matters a lot for things like label bias, for instance. And it matters also for alignments. So to give you an idea, this is a sequence. We have exactly the same acoustic model trained on top with CTC here, with this transcription with CTC, and with this one, the one below, with ASG. And because we don't have these blank labels, and because we are normalizing over the whole sequence, you have a much better alignment just out of your loss function, right? So at the time we did this second paper, we had some good results on LibreSwitch. We were working mostly, and still are working mostly with LibreSwitch for now for transcription. Although, like, the systems based on like HMM DNNs were much better already at the time, still at the time. So now I'm going to present something a bit more. So now we're gonna do some other part of end-to-end learning, which is how to get rid of features of speech features. And so this is basically the corner piece of the PhD thesis of Nel Gabor, a past PhD student of mine who's now at Google, actually. And yeah.
Just a small question about the ASG.
Yeah.
How do you handle repeated letters?
Good. We have a special label, which is actually the character 2 in our representation. And this says that like the model cannot put this, which means repeat the label before. Yes, those are tricky details. Okay, so classic speech features, I guess everybody's kind of familiar, but this is in the one-slide summary for MFSCs, from MFCCs and log Filterbanks. You have your speech signal, you do some windowing, humming very often, over 25 milliseconds, something like that. You step it, you do your STFT, take the power spectrum, you average it over filter banks that are on the Mel scale. You get your log Mel Filterbanks. Okay, so here there is an error, it should be about 40 bins. And then if you do MFCC, you do your DCT. So basically we want to get rid of that, and we want to get rid of that, but we actually want to take inspiration from it. We don't want to just do something random. And actually, again, we are not the first to train neural networks directly on raw waveform. That's even from the 90s. But the work mostly Nel did is to really look at what is crucial in this pipeline that we have, and what is not, or what can be free-moving parameters, and to try and make it end-to-end differentiable. So the windowing, first of all, was replaced by convolutions that are, so windows of 25 milliseconds, you can do convolutions over 160, no, sorry, yeah, I mean, you do convolutions over a bunch of units in the time domain. Oh yeah, 400 samples is written there. 400 samples, and you stride them by 160 to stride them by 10 milliseconds. And so, what you need to do if you're in the time domain and not in the Fourier domain to be able to compute Fourier transforms, you need to have complex convolutions. Very easy way to implement complex convolutions in any kind of framework is to just double the bandwidth of what you would want to have and just use L2 pooling on the output of this, right, over striding of 2. And so that's how we represent complex convolutions. So after that, we have the equivalent of STFTs, and we do some low-pass filtering also with convolutions, and then pooling with log and taking the absolute value, which is similar to what is done in MFCCs, log Mel Filterbanks. And so one thing we have to do is, this windowing, it has to approximate this Mel filters. They have to approximate here the kind of Mel banks the Mel filter banks that we are using. And so to do that, we use Gabor wavelets in the time domain, and the right Gabor wavelets in the time domain are going to match the triangle filters. So here you have the Mel filters in plane and the Gabor wavelets and the effect of the Gabor wavelets in frequency in dashed lines. And if you look at them and initialize them the same way as Mel's, you get this kind of filter bank, which is pretty hard to distinguish. And so first, we just initialize them like that and train the other parts of the model, or train them from initialization. But later, by doing some work on how to properly optimize them, we actually don't even initialize them like that. We still get scales that look like the Mel scale, at least in some bands of frequency, which is really interesting by just training them end to end. So, yeah, I mean, maybe I can go over that, but basically, this is this Gabor wavelet in time domain, and this is its representation in frequency. So, okay, now what we did finally is to put that all together with our pipeline to train from wav2letters. So we have really wave coming in, and then, okay, a few missing bits that I didn't talk about before. We have a pre-emphasis stage, but it's basically a 2x1 convolution. We also have some instance norm, which allows us to basically start with a completely random front end instead of starting with an initialized front end that kind of mimics log Mel Filterbanks. It's important for training and basically for stability during training of those. And then, so this part is what I just described. take the audio and produce something akin to the log Mel Filterbanks. Then we have our, so here we had our, a bit dated now, we have different acoustic models now, but basically stack of convolutions with gated linear units activations that produces a series of letters trained with ASG. And then we also have a language model that is based on stack of convolutions. So it's really convolutions all the way from the raw wave to producing words, except of course we have a bin search, right, with this language model. So that's the whole pipeline of like what we call fully convolutional ASR. So we started by emulate, but now we learn the switch features. Then we have this big convolutional acoustic model, this ASG loss, and the language model. Okay, so the results we get by doing that at the time were state of the art. Well, at the time, yeah, because now if you assisted to the past 18 months of work on LibreSpeech, there was some deconstruction of the benchmark where like the state of the art now is at like 5.0 on Testozer and 5.8 for end-to-end systems, which is crazy. but basically, we even basically reaching very good water rates for the time, we saw a boost by using this learnable frontend. So if you look at the difference between Mel Filterbanks and using learnable filters, we have an improvement both on LibreSpeech and on Wall Street Journal. And on Wall Street Journal, the improvement is much bigger. And my thinking is because it has kind of a regularizing effect. Because Wall Street Journal, one of the really bad things about the setups, in my opinion, is that the validation set and the test set are very different. We have some models where we cross-validate on the validation set that have better results than some other models that we already previously cross-validated on the validation set. And when we look at the test error, they're inverted. So I think here there's a bonus of learning from the raw waveforms, but there's an additional bonus on Wall Street Journal. Okay, so now to kind of give some, put some weight behind saying it's easily hackable and you can study many things with end-to-end learning, I'm going to tell you about kind of a very short study we did a bit on the side of wav2letter, where we decided, okay, traditional state-of-the-art pipelines, they actually do some speaker normalization, either with height vectors or VTLN at least, or stuff like that. And we don't have any of that in our pipelines. So we're thinking, okay, let's try and add a loss for the speaker. And here we were puzzled because actually we didn't know if it would be good for the model to be trained multitask, so have a loss that trains it to do speaker identification, or to be really bad at doing speaker identification. But funnily, it's quite easy. You just add a head to your model, a classifier, and then you say, when you're doing multitask, you actually apply the gradients of the classifier. When you do adversarial loss, you just put a minus between in front of the gradients, and then now you're learning to be agnostic to the speaker, right? To the speaker ID. So we experimented with that with a model where so it's a convnet again, and we put this head for classification of speaker either after the first few layers, or in the middle, or at the top of the network, and we experimented with those. And so those are kind of the results we get when we put it at the beginning. Those are speaker classification accuracy for this model. And remember, this model is trained both to do that and to do ASR, right? So to transcribe. So when you do multitask, you're pretty good at speaker classification. You're actually a bit better when you learn to both transcribe and classify the speakers than when you just learn to transcribe yeah, which is normal. You have this additional loss. If you put it in the middle, okay. So maybe let me explain another way. The baseline is when you don't train anything with the speaker ID, right? So you just train to transcribe. So if you use that, the output of this representation with a classifier to then just train this representation to classify speaker. If you do that on the beginning of the network, you get the red, so you can learn pretty easily from the first features from your network after 2 layers, if I remember correctly, to classify speaker. if you do that deeper in the network, you get worse and worse because the network learns to transcribe, doesn't learn to classify speakers, right? So it loses this ability to do that in terms of representation. When you do multitask, you keep this ability much more over the depth of the network, even though it's multitask, so it's also weighted to do the transcription, so it loses some of this ability. When you do adversarial, which is you try and train your representation to be agnostic to the speaker ID, of course, you're much worse than at classifying speakers. Yeah?
Have you looked at the performance of the baseline out if you train adversarial in? So like you have the adversarial branching out at the beginning, but you're still trying to do speaker recognition at the later.
No, we didn't do that, no. Because we plugged...
See if where
Yeah.
you put the...
We plug this only at one level. What you say is we plug this at this level to train it, and then we plug it at this level.
Apples to apples. So
Yeah,
the
we did.
thin layer, does it impact later on?
Yeah.
if you put it, or
Yeah, we didn't do that. Yeah. It would mean we put 2 of those branches instead of 1. We train this one, and we just look at this one after training.
without training, yeah.
No, we didn't do that. What we found out is... Oh, I removed the ball. So what we found out is actually the multitask is not helping at all in terms of water rate. The adversarial is helping a bit, but again, this is Wall Street Journal, and I'm not sure if it's not just a regularizing effect on Wall Street Journal. And we tried something that actually hurt the performance, which was to in water rate, but it was great for speaker classification, where we added to Wall Street Journal 35 hours of libre speech in a semi-supervised setting. We don't use any of the transcription labels, but we just used the speaker IDs, and we trained the speaker classification part on this. The reason we did that is that the set of speakers in Wall Street Journal is not that big, so we wanted to see if by getting a better speaker classifier, we could get a better effect. That's not that true. So now we have some reasons to understand why it's not that great, actually. It's doing an adversarial loss is too hard a constraint on your network because you ask it to really, so like putting minus in front of the gradient, basically, is too strong for the network as a constraint. You should instead ask your network to have some adaptation layer to adapt to the speaker, and ask for this adaptation to be the identity. So if you want to read more into this, you can read this paper as a starting point, but then I would recommend watching the recent talk of Léon Bautou on basically how to do proper adaptation to different domains. Okay, so then we worked on another part of like end-to-end learning is to say, okay, whenever we do ASR, we work with a lexicon. So we worked on lexicon-free speech recognition. So basically, we always have this, right? This beam search with a lexicon and a language model. And that may be problematic for a few things. One of them is if you don't have a big lexicon or a big lexicon with your language model, you're going to be very bad on out-of-vocabulary words. And there are always out-of-vocabulary words in the wild, right? You have like names, places, numbers, stuff like that. And so we said, okay, let's try and not do it word-based, but remove the lexicon altogether. First, simplest approach we could do, because we were doing wav2letter, is to use actually a character-based language model. So this was a bit before everybody started doing just word pieces-based models. And so the way it works is like that. We use a character-level language model, either n-gram or convolutional. So convolutional language model, it's like it's kind of all ways of doing neural net language models, but it's really similar to an LSTM. You could replace LSTM whenever you see conv LM in these slides, and that would be the same, right? So you preprocess the data to have the word segmentation, because now you're doing letters, right? So we basically add just a word segmentation character, and then we train our character-level language model like that. There's also, if you want to compare language models across word-based language models and character-based language model, you need to make sure that you compute the perplexity in words correctly, because there are different segmentations possible whenever you have a letter-based language model. And so in terms of, so because of that, like basically we can only provide a lower bound and higher bound for the perplexity for the character-based language models, and that's what the lower bound is blue and the higher bound is with the orange. So if we look on perplexity of the language models we train to make sure that we are going to compare apples to apples in ASR later, we kind of got convolutional character-based language models that are in the vicinity of the word-based convolutional language models that we use. And for the n-gram, it's a bit less the case because, well, words are long in letters, so but training a 20 gram is already also, I mean, storing a 20 gram on disk is a bit expensive. So 20 gram doesn't match exactly the word 4 gram in terms of perplexity. But for the convolution, it's kind of okay. Okay, so with enough context, so because convolutions, to give an idea, they have about 55 characters of context. So to have, they have 55 words, but the convolutions based on letters, they have about 200 characters, which is probably enough in terms of context most of the time. So then we did ASR with that. So we don't change anything to the acoustic model. We just change things to the language model. And so those are results on What's the Journal at the top and then LibreSpeech at the bottom. The state of the art at the time for What's the Journal was quite below us, but we compare, for instance, to end-to-end LMMI, which is the state of the art in end-to-end system at the time we published this paper. And they actually also did a lexicon-free study in their paper, which came out like really right before us. But their lexicon-free results were much worse than their word-based results, and word-based and lexicon-based results. So for us, the results we get with n-gram, we have, as we saw for the perplexity, well, we have a bit of, we lose some performance in word rate. But for actually the character-based being, so the green is character-based, but with a word lexicon. And the yellow is character-based, but lexicon-free, because you are not obliged to output words of the lexicon. That's right. Basically, the lexicon is an implicit thing in your thing in the probability distribution over your language model. And so, in this case, like we get slightly better results. Again, Wall Street Journal results are a bit bizarre. If you look in LibreSpeech, we basically have similar results, which means as kind of for the perplexities, we get as good a result with a character-based language model and a lexicon-free language model as with a word-based language model. What's really surprising is actually the way it achieves this word rate. It's a bit worse on some classic sentences. It's actually quite better on the out-of-vocabulary because it's able to output those out-of-vocabulary words. So to give you some examples, this is lexicon-free decoder, so the character-based without forcing the output to be a lexicon, compared to the word-based decoding with the word-level language model with a lexicon. And so basically it's 33% better on out-of-vocabulary words on the clean portion, and it's 14% better on the other, which is called also the noisy portion of LibreSpeech. And you can see what kind of output it gives here. It's even, so this is, like the first line, for instance, it's even considered an error, again, in terms of words. But the output of the lexicon-free character-based model is much better than the one from the word-based one, right? So instead of PKIA, it writes PKIA, but without the H. Too bad. So you still have the same order rate, but it's a much closer word. Sometimes it recovers words completely, where here, like the output from the word-based model is really not as good, right? And again, here you have an example where you have so you still have the same order rate. No, actually, here you have 3 words, so you have even a worse order rate. But you still have two errors here, 2 substitutions, but the words that it produces are much closer from the ground truth. Okay. Now we're going end-to-end, but by really learning through everything in our system. So this is a more recent work that was presented at ICML this year. So again, traditionally we have this, the language model, the lexicon, the decoder, and we train just like that, which is a bit sad. But instead, let's try to train through the decoder. So let's try and have the loss based on the words. This still exists because we need to decode, we need to use a language model, we need to do this to get good water rates. But how can we get gradients through this to train the acoustic model? So we can even, if we are able to do that, get gradients to the language model. If we are able to make this differentiable, we can also train the language model. So this is, let's start back from where we were before with the auto-segmentation criterion, where, as we said, you push up all the possible transcriptions, and you push down, so you have this negative term to the loss, all the possible paths. Well, basically, you kind of do the same thing, but you have to do it by doing ITRB at inference time during the training. So now it's no longer language model free training, it's language model training, because here, what you can add in the scores to the transcriptions is the language model scores. And so again, this is not completely new. Actually, there was work on that called graph transformers networks from the 90s, from Léon Bottou and Yann Lequin. But applied to speech recognition, and it's not completely new also in machine learning in general, because there was some work on machine translation applying that. In speech recognition, it's similar to lattice-free MMI, with the caveat that, so the original lattice-free MMI, it trains with an alignment, and we don't have an alignment here. But the end-to-end lattice-free MMI gets rid of the alignment still. Here you have a language model that is based on phonemes most often in end-to-end lattice-free MMI. And so here we have a language model that is based on words. It doesn't change anything. And so basically the way it goes is like that. So we have this acoustic graph. We have the lexicon. So here it's represented as a tree, right? And we have the word language model. So here we can have an n-gram, but we can also have a neural language model. Here we used only n-grams because for speed during the training, if you have to call forward on a neural net language model, you need to do a lot of optimization. And so basically during the training of your acoustic model, you're doing the beam search the same way you would be doing during transcription. And the way you do your beam search is you augment your hypothesis. So at a given new frame, you augment your hypothesis constrained by A, L, and G. You merge your hypothesis because otherwise you're going to blow up your memory, and you prune them. And this process of doing this, right, those operations, they are basically differentiable. So if you do that on an autograd tape, you can call backward them, and it's going to work out fine. So the original version was done like that with an autograd, but it's a bit slow. So basically, Ronan worked on doing a more optimized version where like the autograd is just partial for these operations. So when you're training that, what it means is you're doing beam search during training. So we do two things. One thing is we don't do a cold start. We start from a model that is a bit trained already with autosec criterion. So that's what you see here. So the top plots these numbers. They show the number of epochs. So at which epoch do you start the training with the differentiable decoding? So those are shown here. So this is the single model. The blue one, we start the training here, because if you want to go from 100% or more water rate to this, you already have a few hours of training. So you start either from 150, 250, or 500 epochs. And that here we do a study of what kind of are the final water rate we can achieve. And so the later you start in train, the better it is. The problem is the later you start in train, the more your model is already stabilized within local minima during the initial training. And so actually you lose a bit in validation. So forking out early for your one start is the best, which is great. It means like you can start training in this mode as soon as possible. And the plots at the bottom, they show the effect of beam size on training. So you need some beam you need some beam to be able to do this training regime. And that's what it shows here. So if you have too small a beam, like if you have a beam of 250, you actually are going to diverge during training. So the reason for that is, maybe if we go back to, well, I think I have the equation after actually. Okay, no. So if we go back to this loss, okay, we are, it's the same. We are pushing up all the weights, all the paths that correspond to the transcription and pushing down all the other paths. The caveat compared to ASG is that we are doing that by taking into account this language model. And so when we do that, or you can see it in your, so you have three terms to actually compute these two terms. One is the logad of all the scores. So the logad of all the scores for your current beam. You also have to, at the beginning of the training, the target transcriptions are not going to be in your beam, right? You're not that good, so they're not going to be in your beam. So you have nothing to push up. So what you need is to add them. So now you're considering all your beam plus all the correct target transcriptions. And you need to not do double counting. And if you do, it completely blows up your optimization. So you need to do logad of all the things in the beam. This one is not good, you're going to push it down. Plus logad of beam inter target, you're also going to push it down. Plus logad of the target transcription, this one you're going to push up. And you need to have this term with for not doing double counting. And so basically because of that, like if you have too small a beam, your target is really not going to be in your beam, and you're just going to keep adding the target transcription to your optimization, and your model is not learning to put the target transcription in the beam in the first place. But as soon as you have a big enough beam, then it doesn't matter that much if you have a bigger beam or not. So in all the experiments we did then for the results in the paper, we used a beam of 500 actually because it's much faster. So what's really cool when you do that is you can train a very small acoustic model, because the acoustic model just has to focus on parts where the language model is unsure. So you start with an n-gram, for instance, a 4-gram on words, right? So this part, your model, when you're training it end-to-end, is already good about that. So you really need to train your acoustic model to disambiguate where the language model could fork, right? And so you can train small acoustic models, I mean small by 2018 or 2019 standards, not by 1990 standards, of course. But so you can train 7.5 or 10 million parameters acoustic models and get some really good results on a bunch of data sets. So this is Wall Street Journal, and this is LibreSpeech again. No, this is Wall Street Journal again, sorry. So here the difference is we didn't even use a language model that was trained on more data. So this one, we use the training data from Wall Street Journal to train a language model, and we train end-to-end the acoustic model with that. This one, we don't even do that. We just have a language model that is trained on just the acoustic transcriptions for the 4-gram. And when we have zero language model, or when we have, so the bilinear part here, we actually train that at the same time as we are training the acoustic model. The reason being it's directly in the loss instead of having a fixed mixing for the language model with the acoustic model. We train this as a bilinear function. So what's really cool is you can really make your acoustic model be good, be strong, or spend its capacity to learn what is important, knowing a language model. You can train both jointly. And to me, the icing on the cake is you don't have to do anything at the decoding, because you already train your model for the best hyperparameters to merge your language model and acoustic model. Like, like the language model weight and the word score, for instance, which are very fun free parameters for the cross-validation step. Well, here you don't, because you just backpropagate to them and you learn them. Okay, and now I'm going to talk a bit about models that go directly to words. So going back to an older study where basically we learned we use some weaker form of supervision to learn to locate and classify words. So this is example sentence from Timit, I guess. And so instead of having it labeled either like that with force element or at least like that with the transcription, we only took the top 1,000 words in the vocabulary and annotated sentences with the bag-of-word version. So we just know which words are there, we don't know where, we don't know in which order, we don't know how many repetitions. And so what we did there, we have a ConvNet again, this was 2015, so we were deep into ConvNet. And we have a ConvNet that outputs distribution and words for each of the frames of his trading. And we have an aggregation stage, which is here log sum x, basically. And then we have a multi-label classification for all the words as bag of words. And if you do that on LibreSpeech, for instance. If you compare it to, so it's actually pretty good, and I'll show in a minute, to learn where the words are, even though it has no information about where they are and what they were represented by, but just because of the joint probability. And so here we also compared it to some fully supervised HMM-GMM keyword spotting pipeline from Caldi, which was pretty good at the time. And we get 60.1 word location accuracy versus 72 for a fully supervised keyword spotting system. But really what's interesting with this system is that, right? So at the bottom, this is the gold force alignment of the words. At the top, this is what you learn when you train your model like that. So you really learn to find where the words are. You don't learn the segmentation, but you learn the localization. Even though nowhere in the loss it was given. And so when we were doing that, the last bit of study we did on this model is we actually did the t-SNE of the acoustic word embeddings of this model. And we found that we have a lot of acoustic similarity for these words. And so more recently, we actually revisited this approach by saying, okay, let's use these word embeddings, let's try and train them end-to-end with our now pipelines that do speech recognition. And so that's what Karen was talking about right before. So we do direct-to-word transcription with a drop-in replacement for CTC and both SIG-to-SIG. So how does it work? At the top, we have the same kind of acoustic models you saw so far for wav2letter, but instead of producing emissions and probabilities over an output vocabulary, they just output in an embedding space. And then we have embeddings from letters for the words, and I'll show the kind of network we use for that right after. And basically, instead of having the scores in CTC, for instance, or the scores in SIG-to-SIG being the emissions of the acoustic model, what we just do for the scoring is just the dot product between these two embeddings. And so here on the right, you have how we embed words from letters. So we actually have, we tried a bunch of things, but we actually just have a small ConvNet of 3 layers for most of the experiments and all of the experiments I'm going to show, with some temporal pooling so that we can handle sequences longer than 5 letters, which would be the size without that for 3 layers of convolutions of 3. And so here, basically, when you input to this CAT, you're going to get one embedding. When you output SAT, you're going to get another embedding. And so one last thing to be able to train that, if you produce a score, you're going to do a dot product between your acoustic embedding and your letter-based embedding. And in itself, it's meaningless, so you need to compare it to some other scores. And if you do that, and we want to do that kind of open vocabulary. So if you do that open vocabulary, you have like an infinite number of words. So we actually just do negative sampling, where we compare it to, for each sample, actually, we just sample, for each sample during our training, so each batch. For each batch, we sample a set of negative samples. A batch is going to be a few occurrences, for instance, 4 or 8 occurrences of LibreSpeech. Well, in this case, we use, for instance, 1,000, 2,000, 5,000, or 10,000 negative samples. So again, here there's a threshold after which it works pretty well. So 1,000 is a bit too little. Your final one error rate is going to converge much worse with 1,000 than 2,000 or more. In all our experiments here, I think we use 5,000. And so this is basically LibreSpeech when you train it like that. So the baseline here is the word piece models. So word piece models are the exact same acoustic models, but trying to output one of 10K unigram word pieces. And those are the scores they give on Decoder, for instance, or Decoder here. And we compare training, we compare those exact same acoustic models with training models to output word embeddings, which is not that, so we didn't get the seek-to-seek to work better than the word-piece-based seek-to-seek, and seek-to-seek is a bit of a different beast because you need to pay attention to the dot products. But for CTC, for instance, it works beautifully. And one of the big advantages of doing that is we can stride our model a lot because the output of the acoustic model is no longer letter or subword units, but it's full word. So we even have pretty good results when we stride by 16, which is 160 milliseconds of striding for acoustic models. That's basically a cheap and an easy way to make the acoustic model very fast. You stride them a lot. Oh, and sorry, and one more thing in this. We're not constrained to a lexicon. So here, the first results where you have 89K for the dictionary in train and in test. You're using the same dictionary at train time and at test time. But because you can produce an embedding for any arbitrary sequence of character here. You can put any arbitrary sequence of character, you get a one embedding. So we also decoded with what we call dynamic lexicon, or it could be lexicon-free, where actually we call it dynamic lexicon because we do input a lexicon, but it's going to be a much bigger lexicon of, for instance, 200,000 words. And then, well, we get better performance just because we can handle some OOVs. Right? Okay, and the last remark on this model. To train those, the regularization of the embedding is crucial. Very often you have optimization problems if you don't handle that properly, and we have the details in the paper. And then we looked at the nearest neighbors for the acoustic embedding space. And what's kind of funny is that it's a mix of phonetic similarity and semantic similarity. So you have things like 8 each day, night, light. So night, light have the same sound. I mean, at least to me. 8 each. So you have some phonetic similarities in a bunch of those. So those were cherry-picked, but not that much actually, right? I just did that maybe a few hours before the deadline. I just looked at the embeddings, printed some nearest neighbors, say, okay, those are good. I didn't have time to cherry-pick them really carefully. And but most of them, when I looked at it, they were really they had either some phonetic or some semantic proximity. Okay, and so we do all of this research in a framework we open sourced, as Shinji was saying before. So originally we were doing that with Lua Torch, and the first version of wav2letter is still out there in the repository, in the branch. And now we are doing everything in C++, and I'm going to tell you quickly about our setup. So basically we're leveraging a bunch of existing things. We're leveraging cuDNN for GPUs and KL for SPUs, ArrayFire, which is a tensor library that already exists, that is out there, NCCL and MPI for communication. And we built a bunch of things on top of ArrayFire, which are basically distributed training, methods, datasets, neural networks, classic neural networks, blocks and activations, and an autograd, because this way we can experiment with arbitrary models. We call this flashlight, basically. And then, on top of flashlight, we built wav2letter++, which is basically a bunch of criterions. Some of them are presented today. The features computation that are done on the fly from Wave. So the decoders for different kind of outputs for lexicon-based, lexicon-free, letters, word pieces, words, all of that. And some recipes to train directly and which reproduce exactly the results we have in the papers and the dataset we showed our results on. So we did a bit of comparison with other frameworks. But as a disclaimer, we really did our framework not because we don't like other frameworks. It's more because we like to have a deep understanding of all the stack of the model, going down to the hardware, to be able to optimize things when we need to. So for instance, the differentiable decoding part that I presented earlier, if we didn't have a clear control on the autograd and how things are actually executed at the C or C++ level, it would be very hard to optimize it so that you can really train it in real time. So other frameworks out there, they're great. Use them. They have a bunch of similar features to ours. One thing we put a lot of emphasis on is efficiency. So this is, for instance, some benchmarks on distributed training for wav2letter++, ESP.NET, OpenSeq2Seq, and OpenSeq2Seq in mixed precision. OpenSeq2Seq is made by NVIDIA, so they try also to make it efficient. And scaling with number of GPUs is much better for much better. I mean, it's a log scale, right? So it's better actually for our framework. We tried. So these are the kind of models we optimized when we really developed wav2letter++ originally. So this is a bit unfair because that's our turf, kind of. But we also tried models that we find in other. So these are models from ESP.NET and Caldi, for instance, which we kind of never used before. So the scaling is great, and that's kind of one of the actual purposes of doing things ourselves. And in terms of decoding, we have a quite efficient decoder also. That's the time it takes you to get to 5% Worley rate. So if you adapt your beam to get to that with a given model and DevClean with the different frameworks, and that's really like having this efficient decoder. So why is it efficient? It's really also because we make some clear choices. If you want to decode with phonemes and with WFSTs in wav2letter, you can't, right? We made these technical choices of making things simpler, but by making them simpler, we can make it faster in some cases we're actually using. Okay, how am I doing for our time? Okay, I'm kind of done, so it's fine. I never rehearsed this talk, so. Yeah, so again, this slide, end-to-end, why do we care about end-to-end models, end-to-end training? I hope I convince you that for some things it's simpler, and simpler either to optimize or to apply to a bunch of different things or to scale up. And I hope, so this I think people agree, it's just that it's kind of non-controversial, but I hope I convince you that it's also more applicable for doing some research, not all the research, but some research at least, where you can really take a model, change something, look into just that by doing end-to-end things. So just to open discussion a bit, maybe what's the future for end-to-end ASR? I would say even more end-to-endness. I think the recent results of Seq2Seq models without an external language model show that maybe with the right regime of training, we don't need that much of a language model and decoder anymore. Of course, we're going to go towards less supervision. Supervised data is hard to come by. When you're in resource-rich languages like English, French, German, Japanese, stuff like that, it's easy. But if you want to cater to a long tail of languages, you need to do more with less supervision. More tasks, because, I mean, ASR is not the end of everything you want to do. More languages, code switching, this kind of stuff. I think all of this is coming to ASR. We already to end-to-end ASR. We already saw papers on that. And for wav2letter in particular, wav2words is something we're working on. We publish some papers. We are releasing some code about that. We are pushing out new acoustic models, some smaller ones, some more robust ones, some pre-trained on more languages. We try to, whenever we can, due to the license of the dataset, we also provide pre-trained acoustic models. And of course, we are doing research on using less supervision. Okay, thanks for your attention. I presented work on this people.
Question? My question is, you guys, you also use some sequence attention-based model, but maybe CTC or ASD, right? So, what kind of a reason or policy or to kind of stick to that kind of a method rather than the attention-based?
So it's mostly historic for us, I would say. But actually, like there was a deeper study of Seq2Seq models and wav2letter led by Oni Hanun earlier this year. And now we are doing we submitted much more work based on sig-to-sig models, and we have pretty good success with sig-to-sig models. One thing that is a bit tricky is we had to get some time to really understand how to properly optimize models with sig-to-sig models, whereas like sig-to-sig, CTC, we already did that, or actually it's maybe a bit easier to optimize. But now we are doing that. Yeah, we are doing most of our recent papers. They have results both for CTC and for sig-to-sig. Yep.
For the domain adversarial loss, you mentioned that could be a problem because the gradients are too strong. Could you comment on like simple methods like maybe scaling this down with a lambda or having kind of like
Okay, so we did scale things.
something like this?
We did scale things down with a lambda. The problem is not that it's too strong in terms of gradient norm. It's too strong in terms of the requirement you ask your model. So to make the picture simpler, it's like when you are doing multitask, if you are trying to make your model be able to classify speakers, it's like if you are trying to make two vectors collinear, which is fine, right? When you are making it adversarial, you should try and make your vectors orthogonal, but you're actually trying to make them antilinear, right? So it's a much harder constraint than what you want from, because making two vectors orthogonal in a big high-dimensional space is super easy, right? You just need one dimension. So here, basically, we were a bit naive by saying, okay, we can just do this, right? But what we need really is to make it agnostic, not without making it adversarial to the speaker. And if you want to dive more into that, you should really watch the talk of Leon Botou at ICLEA this year.